today's lecture is even more important than the previous two. You'll see very soon why. Because this field did not exist, really, did not exist before a great discovery called the boundary layer theory. Chapter 2 begins with the first three equations. While facing the challenge to predict mathematically, that is, by invoking these principles, to predict the flow field, hand in glove with that is the pressure field. As I said later in the course, the temperature field. But I'm not going to rush with the mathematics because you've been through that sort of torture many times in your education. I have to say a few things about purpose. Why are we, studying convection? I already mentioned the fact that heat transfer is this phenomenon of energy flow that's invisible, but it happens when there's a temperature difference. There's a payoff from being able to predict the relationship between temperature difference and heat transfer rate. That is the problem to solve, or let's call it the secret to know, because after you learn the subject correctly, you become very powerful. You don't have to go through a headache anymore. And two things. Convection, the subject is a discipline. Discipline in English comes with positive and negative connotation. Somebody is disciplined, and that person is exmatriculated, you see, or in church excommunicated. That's the negative version. The positive version is that you become a very good player, okay? You did, or for that matter, a very good soldier. A very good friend of mine who was in the Vietnam War told me that when he was in boot camp, the sergeant would shout at them, "Remember, there are only two kinds of soldier, the quick and the dead," which meant pretty, well, I'm not going to translate that for you, but the point is that was part of instilling discipline in these young men. It's almost, not exactly, but it's similar here. Discipline is, convection is one example, a distinct body of knowledge. Not to be confused, convection, not to be confused with, say, dynamics in mechanics. This body of knowledge is relatively simple because it has, I wrote here, very few precise words and rules, also known as laws. You saw only a few here. They are sharp and crisp. They don't lie to you. They're always written this way. And it is a body of knowledge enrobed in promise. Promise is like a very good coat in winter. You are much better off when you possess the discipline. So promise. Now, promise to do what for you? Well, if you know it, you'll discover that you receive what was promised. I mentioned earlier, you become powerful. You do not waste time. You you have a lot more time to move on and enjoy the other disciplines that you acquired in your training. So convection is a discipline. In this course, the discipline one, which is one, is taught several times by invoking several domains of application in which the promise is emerging. And we begin the course with, in fact, this sort of structure of the course is a drawing that I made not long ago. I'll make it here. Leave this area available a little bit wider. We will divide the domain of applications into, first of all, into two. One is called forced convection, and the other one, natural convection. Forced convection is a flow that is driven by power. For example, a fan rotating and blowing air through tubes or across your face in air conditioning. So that's forced convection, or for that matter, dragging a body through a fluid. That's a different frame of reference. It's the same flow. Relative motion, solid versus fluid, as in the case of a boat powered by an outboard motor or the wing of an airplane, all right? So that's forced convection. Natural convection is where the flow happens by itself. You'll see soon that's a flow driven by buoyancy. It is one that you find on a planet with the gravitational acceleration that's let's say, meaningful, a planet with the fluid on its surface. By the way, the planet is all fluid, so watch out. You are, walking on one. Earth is mainly a ball of fluid. We live on the crust. Yeah, how thick is this crust? Did you ever think about it? Anybody? How thick is down there?
20 miles.
How many?
20 miles, I don't know.
20 miles, not that's close, yeah. 20 miles is 30 kilometers. The average thickness of the crust is 40 kilometers. That's really a thick crust. Well, I'll tell you how wrong that impression really is. I know another thing with a crust like that, and that's a fresh egg. A fresh egg has a very skinny eggshell, right? So I just went through this calculation 2 nights ago to prove to myself how wrong I was to think that the Earth's crust is thick. So there's a ratio of eggshell thickness to egg radius, and there is a ratio of Earth crust thickness to Earth radius. So in relative terms, I mean, both shells, the crust and the shell are thin, small meaning compared with the radius, but the Earth's eggshell, quote unquote, is only 1/5 the thickness of the eggshell. So it is like Earth is wearing a solid film, or a thin ice that's so thin that it is constantly breaking. And on this blob, the yolk of Earth, these very thin pieces of that shell have broken, and they're bumping into each other, which is, of course, what's been happening to the so-called plates, the plates that keep flowing and changing the geography. The geography is looks like static today, but it came from an older one, and it's heading in a predictable direction. So think about that. Careful, not to fall through the crust. The other way to divide the material is to recognize that when you have a relative motion, it depends on what flows relative to what. I mentioned the boat and the airplane wing, that is a configuration of convection where the flow embraces the solid. The flow is around the solid. So that's called external, because the fluid is external to the solid, and we reside on the solid. We are not fish, you see, but even the fish is experiencing convection because the fish is somebody, has to exert power in order to keep on living. The opposite of that is the configuration where the solid surrounds the flow. And that is called duct or pipe, conduit, and so on. And on this table, I call it internal convection. All these heat exchangers you hear about, or sometimes you have to work with them, buy them, design them, do all these things, are just like the human lung, architectures filled with internal convective elements. So that's the structure, which is why these chapters in the book have titles of this kind. The beginning is always meaning. The wise presenter is the one who tries the simplest first. And the simplest way to predict convection is to assume that the flow is laminar. Laminar. I'll explain laminar soon. In fact, I'll do it right away. The word laminar means what? I think those of you who took my courses before probably remember.
Knife-like.
What?
Knife-like.
True. Correct. That's right. You're actually not long ago shaving with a blade, and the blade in Latin is lamina. So blade, and that means that the flow that's happening is like blade sliding on top of blade, without eddies, without overturning, without complications, without fuzz. So that's laminar. This is the slow kind of flow, if you want a feel for where to look to find it. So that's the beginning. I just mentioned the next version. The next version is the same package of lessons for turbulent flows. So turbulent flows. You can treat turbulent flows intelligently if you know how to treat laminar flows. And if you know the structure of the domain, basically if you know the four slices in which the discipline has segregated itself. And then the third page of this multi-page treatment has to do with the fact that the first two versions refer to a fluid that is always single phase. That means always gas, always liquid, or for that matter, always solid, if you're talking about the movement of a solid along another solid, such as the ground meat into and through the casing of a sausage, or the bullet through the barrel of the gun, or the bullet train through the tunnel. All these things could be solid and solid. The point is, it's just one phase. In other words, there is no melting, there is no solidification, there is no boiling and evaporation. Those are complications. And the third version of the same treatment is called two-phase flow. Boiling, condensation, and then melting and freezing. And the course will end with, in this, meaning the course proceeds from the one page to the next, and by the time you get to the third, you'll know what to expect.